Hello, today we're going to do some examples and have a discussion about Faraday's law. It doesn't like that I write too big. Oh well. To begin with, we're going to discuss voltage versus EMF. What exactly are they? What's the difference between the two? And all of that. So Faraday's law relates two things: an induced EMF to a change in the magnetic flux. I'm going to write changing through some surface. So the induced EMF is around the border of a surface or around a circuit. And the flux is through surface defined by that circuit as the boundary. So if I were to draw a picture of that, that would look like this. We have some sort of circuit and it has a direction that's defined around there, which means that this whole inside bit is the surface. Let me say I'm going to make that be a blue surface. And then there's some magnetic field with at least a component of it that is normal to the surface, so that there is a magnetic flux happening. And that is the situation that we're talking about. So, but the question here is, what is exactly an EMF? It means EMF stands for electromotive force. But that's not particularly informative. It has units of volts, but it's not the same as just a general voltage. And that's not very informative either. The way to think about this is that voltage is a sort of general term that can describe things like this voltage source and the voltage drop across this resistor. However, EMF is a specific term that only describes voltage sources. So EMF describes a source only, and voltage can describe any voltage drop or voltage increase across any sort of distance or surface or anything. So there's the difference. What we're talking about with Faraday's law is that if you have a situation with a changing magnetic flux, and there are a lot of different types of situations where that can happen, then you will have an induced EMF. So that change in magnetic flux will cause something that looks like a voltage source to occur. We're going to look at that today in example 6-3, which is a Faraday disk generator. In particular, this is going to be an example of a concept called motional EMF, which happens when you have a conductor moving through a static magnetic field. It might look like the flux is not changing. However, you still have an induced EMF, and we're going to discuss how that happens. So, first I'm going to tell you about motional EMF in general, and then we're going to come back to this problem, example 6-3. So, if we have some sort of magnetic field, and we also have some sort of conductor, let's say maybe a conducting bar, that is moving with some velocity through the magnetic field. This will generate a voltage in the conducting bar. Think of it this way. In the reference frame, so there are charges in the conductor that are moving, and those charges experience a magnetic force, which is Q times the velocity cross the magnetic flux density, as usual. Even though in the reference frame of that conducting bar, if you were moving at the same speed as the bar while you were observing this situation, you wouldn't actually observe that the bar is moving, so how can you have a force happen? Here's the trick. If you are in the same reference frame as the magnetic bar, you have an effective electric field, which is equal to U cross B. So that then the charges in the bar experience the same force as an observer who's not moving would observe to be happening, except this time it looks like it's an electric force, which is equal to QE. It's just that that electric field is given by U cross B. So that means that then there is going to be a voltage, and if you pick 2 points on that bar, 2 and 1, the voltage between those 2 points, in fact, the induced EMF between those 2 points, is equal to the integral from 1 to 2 of U cross B dot dl. People are looking at the pictures of my baby on Google Play. That's what that notification is. You might notice that there is not a minus sign in front, and the general form of this integral is v equals minus integral of E dot dl. That's because for this we would have switched the bounds. We would do the integral from 2 to 1, but instead it's from 1 to 2. So, anyway, hopefully that helps with the motional EMF issue. Here's an important thing. If that moving conductor is part of a circuit, then the EMF that's generated is going to be the integral around the entire closed contour of the circuit, U cross B dot dl. Here's the thing though, if some parts of the circuit are moving and other parts are not moving, only moving parts contribute to EMF. Because other parts have zero velocity, so this cross product becomes nothing. All right, so back to the problem. The problem that we're dealing with right now is called a Faraday disk generator. And what that looks like is you have an axis, you've got a disc, this whole thing is made of metal. The disc is spinning around its axis with some angular momentum omega. And then we have contacts that we make using little metal brushes on the axis and also on the edge of the disc. And then we measure the voltage between those two contacts. We want to know what that voltage is going to be. Let's also define a particular circuit on this diagram, okay? So I'm going to change my color so this is easy to look at, and then I'm going to label some of the points on here. We're going to say that our circuit goes from 1 to 2 to 2 prime. 2 prime is the place where the brush contacts the disc on the disc. To 3, which is also a point on the disc. To 4, which is the place where the disc hits the axis there. To 1 prime, which is that top brush. So, only the part that goes 2 prime to 3 to 4 is made of the disc which is moving. Everything else is not moving. But in addition to that, for 2 prime to 3, that part where you travel along the edge of the disc, U is phi directed. And dl is phi directed. So since U cross B is perpendicular to both U and B, U cross B is also perpendicular to dl, and U cross B dot dl is going to be 0 for the portion that's between 2 prime and 3. But for the part that connects from 3 to 4, that is not going to work out to be 0. And that is what the book means in this example when they say only the path from 3 to 4 cuts the magnetic flux. Doesn't make sense what that means until you look at it and see that the velocity and dl are pointed in the same direction for the 2 prime to 3 path and not for the 3 to 4 path. So on the 3 to 4 path, again, that's the path from the edge of the disc to the center. Here's 3, here's 4. What we have then is U is equal to A hat phi r omega, omega being the angular velocity. dl is equal to A hat r dr. And so that contribution of the contour integral is going to be A hat phi r omega cross B was A hat z b naught dot A hat r dr. Whoops. And that goes from 3 to 4. And that's going to give us what our voltage was, our induced EMF. Now, Let's do this out. It's not that bad. This is an integral with respect to r, and we are traveling from r equals b to r equals 0. The cross product of a hat phi and a hat z, a hat phi cross a hat z is just going to be equal to a hat r. And then a hat r dot a hat r is going to give us 1. So what's left is r omega b naught dr. The omega b naught don't depend on r, so then our EMF is equal to integral from b to 0. Whoops. I was going to move those constants out to the front. Omega b naught. There we go. R dr. We can flip the bounds on this integral by reversing the sign. So that's equal to minus omega b naught integral from 0 to b of r dr, which evaluates to EMF is equal to minus omega b naught r squared over 2 evaluated from 0 to b, which is minus omega b naught little b squared over 2. That's your induced EMF. So the faster you spin the disk, the